Okay? And what we're going to do is we're going to recurse down on the structure of the program. Okay, so programs are kind of a tree. You know, at the top we have maybe a composition of a couple of statements, and then some of those statements might be assignment statements or if statements, and if they're if statements, then they contain statements, and loop statements also contain statements. So we have this whole tree of commands or tree of statements that that we want to operate on. So we just start at the top of the tree and we work our way down to the leaves of the tree. Okay, when you get to the leaves of the tree, there's assignment commands, and we looked at these before. I'm not going to go into assignment commands now, but if you're not clear on it, then send me a message or review the notes. And the other kind of leaf we have is skip commands, which are not very interesting. They do nothing at all. And then we have we have sequential composition, which is nothing more than, well, technically two commands in a row, but one of those commands might itself be a sequential composition, so then that contains two commands, and so on down. And so if you have a string of, say, 5 commands in a row, we just call that 4 sequential compositions. And it doesn't matter how you bracket those. It all works out the same. Okay, so sequential composition, basically we just need to dive down and get verification conditions from each part. So, for example, here we have a sequential composition here, right? And if I was analyzing this, then I would dive down and say, okay, we'll take this as a sequential composition. We've got 1, 2, 3 commands. So there's really 2 sequential compositions. I'll just group it this way. So our first command and first proof outline is this, and the second proof outline is this sequential composition, and then that itself breaks down into sequential composition of 2 assignments, right? Okay, so if I'm breaking this down from top down, so I use my sequential composition rule and say, okay, well, I need to show that this is correct here. This first triple is correct, and I have an assignment command that does that. So I can get my verification condition using the assignment command. And then the second thing that I got to do, according to my rule here, is I have to show that that this sequential composition is correct. And then recursively using the same rule, that means I have to do 2 things. I have to show that this triple here is correct, and then finally I have to show this triple here is correct. So in the end, all I end up doing is applying the assignment rule 3 times, and I get 3 verification conditions out of those 3 assignment commands. Okay? So every assignment command in your program is just going to end up leading to 1 verification condition. All right, let's scroll down a bit. Okay, so let's look at if commands. So we have a rule called the alternation rule, and it deals with if commands. So we'll apply this when we're looking at an if command, and the if command is going to look like this. It's going to have a precondition, which P, and what I call an if guard, E. It's a Boolean condition. We'll have an internal assertion Q0, then some command S. We'll have another internal assertion Q1 for the else part, and then we'll have T, which is the actual command to execute in the else part. And finally, we have a total, the overall precondition or postcondition is R. Okay, so that's the postcondition for the whole if command. Now, so the S here, that could be some compound command. It might just be something simple like an assignment or a skip, but it might also be a compound command like another if, or it might be a loop, or it might be a sequential composition. It doesn't matter, okay? It's going to have, if it is a compound command of some sort, it will have internal assertions of its own, right? And then we're going to stick this precondition on as well. There's no postcondition because the postcondition for S is simply R, right? When S is done, R better be true. And so I'm not going to write that again there. That's implicit, that's the postcondition for R. And there's also the postcondition for T. The postcondition for T is also R. Okay. So how do we apply this rule? Well, okay, here we have an if command with a precondition and postcondition. We want to show that it's correct. Okay, so to do that, we're going to boil it down to a set of 4 verification conditions. Now, 2 of these verification conditions come from this rule, and 2 will come from recursing down and doing the assignments. All right. So first off, according to our alternation rule, we should show that P and E implies Q0. So P is here and E is here. So we can join those, and those together should imply Q0, which is here, right? Okay, so let's look at what happens when we do that. And I'm just going to switch over to my, just going to switch over to my ungapped notes here. All right. So from our if rule, the first thing we need to show is that P and E implies Q naught. So here it is. We have, here's the P, and here's the E, and we need to show that it implies Q naught, which is all of this, right? And it turns out you have to show that something implies itself. Well, that's always going to be true, right? That's, because if the antecedent is false, then the consequent will be false. We have false implies false, false implies false is true. Otherwise, if the antecedent is true, we have true implies true, and true implies true is always true. So, so that's going to be, so we have to show that's universally true, which it is. Okay. Second thing, we have to show that P and not E implies Q1. Okay. So that's what we got here. So here we have here's our P again, and then we have and not E, so that's here, and we need to show that implies Q1, which is here, and we need to show that that's universally true. And it's a little more complicated this time, but again, it is universally true, it turns out. Okay. And then the 2 other things we need to show are we need to recursively show that that this proof outline here is correct and that this proof outline here is correct. Now, in this case, S is just an assignment and T is just an assignment. So what we need to do is recurse down, and we'll end up using the assignment rule to show those. Now, I haven't actually done that here. I've just listed these 2 obligations that come out of the if rule, but following those down, I would then apply the assignment rule to those, and I'll get 2 more verification conditions. And it turns out that those verification conditions are also universally true. So, in fact, this proof outline is correct, and we can prove it's correct using our rules. And then we got really the most interesting one. Well, okay, sorry, before we get there, we got the one-tailed if, right? But that's really just a combination of the two-tailed if and a skip, right? So what if the else part was skip? Well, in that case, you'd have to show that P and not E implies R. And so that's what we have here. Okay? So one-tailed ifs are not too complicated.